Hello, and welcome to our team's proposal for a Ceres sample return mission known as Mission Cereous. The Cereous mission team is composed of 5 dedicated classmates from Professor Lantoine's Orbital Mechanics lecture. This presentation will cover a brief overview of our mission along with an introductory slide providing some information about its background. We will also explain how we modeled our final mission design, providing you with all the necessary calculations and results obtained from our research. Our main goals are set to be achieved in the following order. First, we will launch our spacecraft from Earth and head to Ceres. Then, our spacecraft will orbit Ceres in a polar sun-synchronous orbit, flying over both poles of the dwarf planet until the right time comes to drop the lander on the desired location to collect rock samples. Afterwards, the lander will launch from Ceres to dock with the spacecraft and return those samples home to Earth. Conceptually, our optimal date of departure is on June 11, 2025, and we should complete our entire mission in 9 years and 6 months on December 11, 2034. Previously, NASA launched a robotic spacecraft named Dawn back in 2004 to learn more about Ceres. During their mission, they discovered that Ceres may have an internal liquid water ocean right beneath its crust, suggesting that the planet could be the most water-rich body in our inner solar system. Unfortunately, the Dawn mission ended this year on November 1, 2018, because the spacecraft was running out of fuel. Thankfully, with the information Dawn gave us about Ceres, we are inspired to make another space mission to bring back home a sample of this planet. The following software was used to help our team accomplish our program mission goals. We used MATLAB, Trajectory Optimization Tool, and FreeFlyer. Locator is the optimal landing destination for our lander because its bright cluster of white spots is believed to be made from salt that was left behind when an ancient geyser spewed brine water from its oceanic core. A rock sample from the spot can provide solid evidence of remnants of brine water that once broke through the surface from a global ocean deep inside the crust. On this slide, you can see what will be discussed on our modeling assumptions for the entire space mission from the launch vehicle to Earth arrival. Our team decided to use the Falcon Heavy expendable for our launch vehicle because it can carry our payload into a hyperbolic trajectory away from Earth at a cost of $150 million. Our decision was based on how much mass the rocket can carry at a proposed C3 of approximately 39 kilometers squared per second squared. Our spacecraft will be based on a smaller design of the Mars Science Laboratory re-entry vehicle with a return capsule weight of 70 kilograms. It will be equipped with an abrasive heat shield for safe re-entry into the Earth's atmosphere, plus parachutes that deploy in time before landing in the Pacific Ocean. For deep space travel, our spacecraft will use NASA's evolutionary xenon thruster because it has the highest ISP and highest thrust compared to other ion thrusters. The solar panels along the side of the spacecraft will harvest sunlight from the sun and use the electricity produced from the solar panels to recharge the engine during flight. Although ion thrusters are optimal for space travel, they cannot produce a large enough change in velocity when the spacecraft must slow down while arriving and leaving Ceres. In order to give the spacecraft the boost it needs, a chemical monopropellant rocket thruster will also be installed. The lander on Ceres will have a total mass of 1,361.05 kilograms. The lander will need to be equipped with 3 hydrazine monopropellant thrusters for both a soft descent on Ceres and takeoff to return to the mothership. The lander will also have a built-in mechanical arm to dig into the crust and gather rock samples. 3 hydrazine thrusters will be mounted on a 3-axis stabilized gimbal beneath the lander so that they always point vertically to ensure proper landing and takeoff. Each thruster can produce 400 newtons of thrust with a specific impulse of up to 220 seconds. We utilized the Lambert problem to calculate our spacecraft trajectories from planet to planet, using the Sun as the center of our coordinate system. If we know the flight time from Earth to Ceres, then Lambert's problem is used to find the trajectory joining Earth and Ceres. These trajectories are determined once we find V1 and V2 using the Lambert MATLAB code. Some physical constants include the radius and gravitational parameter of each planet. These values helped us solve the formulas used to generate a porkchop plot and determine the optimal date of departure for our spacecraft. To generate all the values needed in calculations and results of a porkchop plot, the following method was applied. First, we gathered the position vectors of each planet, Earth and Ceres, from horizons to produce a grid of different launch and arrival dates. We then calculated the launch mass as a function of C3, gathered our time of flight for each launch and arrival date in seconds, and computed the insertion change of velocity around Ceres. Finally, we found our mass delivered. In the end, this is the porkchop plot we were able to produce. The C3 value ranges from high to low, low being the color blue and high being yellow. To conclude our method of technical calculations and analysis, we used Lambert's problem for departing from Earth and arrival at Ceres, as well as departing from Ceres and arrival at Earth. The calculations for finding the change in velocities for ascending and descending the lander on Ceres helped find the total mass of propellant used from the landing module and the total fuel mass used up by the spacecraft. To finalize our design, the Falcon Heavy expendable will be used for a launch from Earth to head to Ceres. Ion thrusters will be used during cruise. The spacecraft will fly to Ceres and orbit Ceres while deploying a lander vehicle to go down and grab rock samples from the surface. The lander will launch from Ceres and dock with the spacecraft, then return home to Earth. Using our porkchop plot, our team selected a reasonable C3 and chose our launch vehicle based off the C3 value and the trade study conducted. From this, the departure Julian date from Earth and the arrival date from Ceres can be grabbed from the MATLAB code. This data is similar to the results received from a similar mission ran on the OHM trajectory optimization tool, where we leave Earth on June 6, 2026 and arrive at Ceres with a velocity of 5.864 kilometers per second. We arrive at Ceres on a near-polar orbit on September 14, 2026. The orbiter will orbit Ceres for a month before initiating the lander sequence for the sample mission. In order to know when the orbiter is directly above our landing site, we simulated an orbit mission using FreeFlyer, where we created a ground station that will contact our orbiting spacecraft that is located at the center of the crater. We ran the ground station simulation for about a year, and the average time of contact between the spacecraft was roughly over 1 month. This will be the time interval when we will launch our lander and we will ascend back to the main spacecraft. On October 10, 2026, the spacecraft orbiting Ceres will initiate the separation command so that the lander may descend upon its targeted location. The lander will then initiate its first fuel burn to undock with the orbiter at a magnitude of approximately 96 meters per second. This maneuver will ensure that the lander descends in relative freefall motion. Right before impact, the lander will carry out its second burn at a magnitude of approximately 164 meters per second. On November 17, 2026, the lander will conduct another burn at a magnitude of 164 meters per second to launch itself off the surface of Ceres. Once the lander reaches the orbiting altitude of 50 kilometers, the lander will conduct its final burn at a magnitude of 94 meters per second to rendezvous and dock safely with the orbiting spacecraft. The image on the right shows the return trajectory departing Ceres on July 17, 2033. This date was determined by using another MATLAB code for the return, home, and transfer seen in the appendix. The code does an iterative method to find the minimum delta V required to return to Earth while finding the optimal date to do this. This is a trade-off for mission fuel and weight requirement. However, it is extending our mission life by several more years. This is why the spacecraft orbits Ceres for an additional couple of years, taking photos and measuring data before it departs on its 1 year and 4 month mission back to Earth. In conclusion, our mission plan shows a successful space flight from Earth to Ceres, where we depart on June 11, 2025, and arrive at Ceres on September 14, 2026. Using multiple computer programs such as MATLAB, FreeFlyer, and Trajectory Optimization Tool, we were able to meet our mission requirements. We arrived back at Earth on December 11, 2034, completing the mission. Overall, Mission Cereous would be successful in returning samples from the planet Ceres, allowing us to learn more about this dwarf planet.